In this video, we're going to discuss the dependent samples t-test. The dependent samples t-test is also sometimes called the paired samples t-test. And this is a hypothesis test that's used when you have two related groups of individuals or two groups of measurements where the measurements in one group are related to the measurements on the other group, right? Research designs where this happens include like your pre-test, post-test designs. So let's say if I had, let's say, one group of individuals, I give them a pre-test, then I implement an intervention, and then after the intervention has taken place, I give a post-test. In a design like that, we're able to see that the pre-test measurements are related to the post-test measurements because they're on the same individuals, right? That would create a case where we would use the dependent samples t-test. Another case would be an example like the subjects are matched or paired in some way. So an example of that would be let's say we're studying something, some quantitative variable, but we also measure individuals on other variables before the study, right? And we match the individuals that are closest on those variables and they create pairs or matches, right? That's another way that we could end up analyzing data using the dependent samples t-test. So I can use the same person and measure them twice, or I can pair or match individuals, and then one person may get one intervention, the other person may get the control, or one treatment and another treatment, and then we may compare at the end. Those measurements on the matched individuals are like having the same person, right? So they're dependent on each other because we match them so that the individuals are as similar as possible. So that's another dependent sample type case. In either design, the benefit of using the dependent samples is that we can reduce subject to subject variability in a way that the independent samples t-test cannot. So when we know that we have dependent samples, we should never, ever, ever decide to use the independent samples t-test. It is not valid for those types of problems or research scenarios. All right. So I have an example here. It says researchers investigated whether a flipped classroom model as compared to a traditional classroom model affects the amount of time AP chemistry students spend studying outside of class. And so in this type of study, the researchers decided to match or pair students based on the following variables. They took the student's GPA, their previous science course final exam, their previous math course final exam scores, and the previous test scores up to that point in their current AP chemistry course. Students in one section of the AP chemistry teachers' courses were in the traditional instructional model, and students in the other section were in the flip model, right? And so we have some results of this study, right? We have the hours that students who were in this traditional model of instruction were under, and then we have the hours spent studying for students who are in the flip instructional model, right? The person in the traditional model with this score is matched or paired based off of these several variables here with the individual in this course in the flip model, right? So this 4.97 is related to that 4.19 because we've matched these individuals on these variables here. And there are different types of matching methods that can be used, and that is not explained here, but this led to these matches. So the person who scored 4.78 in the flipped classroom is matched with this individual, and I say scored, but who indicated that he spent 4.4 hours outside of class studying, so on and so forth. Now, what we could do is we can get the mean, the sample mean for our traditional group. That was found to be 4.60 with a standard sample standard deviation of 0.62. And in our flipped classroom, I'm sorry, but my X bars are the bars on those X's are kind of shortened here, but this is your sample mean for your flipped classroom. They spent on average 4.04 hours studying outside of classroom with a standard deviation of 0.66. And so let's say our researchers erroneously conducted an independent samples t-test using this data here. So they ignored, and we don't want to do this, but let's say that they ignored the dependency in that data, and they tried to use the independent samples t-test or the two sample t-test. Well, and they were using this null hypothesis here, right? That mu sub traditional, so the mean number of hours for students under the traditional method is equal to the mean number of hours in the flipped method. And our alternative hypothesis is that they are not equal, meaning being in the flipped classroom actually makes a difference. Those two things are the instructional method is related to the amount of time they spend studying. All right. Well, I ran this using an independent samples t-test. We can already see from the sample data that those in the traditional instructional method, they spend a little bit more hours compared to those in the flipped instructional method. However, we want to do a hypothesis test to see if that's significantly different. And so our test statistic, if we were to use the independent samples t-test, would be 1.9291 with degrees of freedom equal to 18, and this will be the p-value. If we're using the significance level of 0.05, we're going to see that we will fail to reject our null hypothesis, and we see that there will not be enough evidence to conclude that there's a difference in the amount of time that the students spend studying outside of class. For those AP chemistry students, right? And so that will be the results we would get if we were to do this using the independent samples t-test. However, I want to look at this data a little bit more deeply here. I've created a graphic here. You can think of these as almost as like dot plots, but I'm vertically stacking them per group and referencing my axis vertically, right? So I have the test scores, not test scores. So this should not be test scores. This should be the number of hours that those students spend studying outside of class. So I do apologize for that there. This should be the number of hours. But I see that these are the number of hours spent studying for those students in the traditional classroom. And these are the number of hours spent studying for those in the flipped classroom, right? Now, whenever we view the data independently, right, we ignore the dependencies in the data, right? Now, our goal is to see if being in a flipped classroom basically impacts the amount of time studied, right? And if I look at these matched pairs, I've connected the actual pairs by a line segment. Notice how all of these line segments are decreasing. All of these line segments are decreasing from traditional to flipped. And if I look in my chart here of my data, we can see that all of the flipped number of hours completed are smaller or less than the number for the traditional classroom. That actually provides evidence that the flipped classroom instructional method is related or associated to the amount of time students spend in classroom. Now I'm saying related and not impact. I'm not using the word impacting or causing the effect because this isn't a true experiment or what have you. So, but I am saying I can see that in generally I see a decrease in the amount of time students spend studying outside of classroom with this diagram here, which means that I should see a significant result. But my independent samples t-test did not do that. All right. And the reason for that is because when I view the data independently as two independent samples, it's like me not seeing these line segments here. And I'm just looking at the spread of these points here. Notice how some students in general in the traditional classroom spent a large amount of time outside of the classroom studying, while some spent a little bit of time, right? So there's a lot of variability in between each of those subjects. That's what I'm calling the subject to subject variability, right? The same thing happens when I look at the flipped classroom. Some students in the flipped classroom spend more hours than others, right? This student here spends a lot more outside of the classroom compared to these students here who spend fewer hours outside of the classroom studying, right? And so when we look at the data independently, it's taking these measures of variability in the two groups separately into consideration versus, so what that's going to do is increase the overall variability, and the more variability that's in our data, the more likely we are to not be able to see the actual effects that we want to actually see, right? So it makes it harder to detect the effect of what we're actually trying to study. All right. And so our alternative to that would be to remove that subject to subject variability. I know some subjects are going to be higher on the variable, some subjects are going to be in the middle, some subjects are going to be lower. But once I have that dependency here, I don't care how high the highest student is or how low the lowest student is. What I'm going to want to focus on is the differences, because that's actually getting to the effect of what's under studying, right? So that should lessen our variability and make it easier to actually detect an effect in our data. I know we spent a little bit of time talking about statistical power, the power to detect that we're going to reject a null hypothesis when we should. That happens, that increases when we look at or remove that subject to subject variability and lessen that variability overall. All right. So the way we're going to do that is, instead of looking at these scores separately for the two groups, we're going to create another variable known as the difference. We're going to have a bunch of different scores that's going to be given by the notation capital D. These are different scores. And all we're going to do is take the actual value of that quantitative variable under the traditional method and subtract for that the value under the flip method. If I do that, I get 0.78 here. So the difference score for that first individual is 0.78. And then we can do that for all of our individuals, right? We can get a mean of these different scores and a standard deviation of these different scores, right? So the mean of these different scores is 0.556, and the sample standard deviation of these different scores is 0.17. Now, as you can see, if we look at these independently, we have, your standard deviation is the square root of your variance, right? So, but it's still a measure of variability. They're larger when I look at them separately as compared to when I look at the difference. And that's making evident that we're lessening the variability so that we can truly detect the difference. Now, I do want to make a note about notation here. And this is something that I've been struggling with our textbook. Some of the notation isn't consistent to what we use in general in statistics, and I do apologize about that. But X bar sub D is the average of the differences, and what your textbook is using for the standard deviation of the differences is just plain old SD. And so note that this is the standard deviation of the differences when we're talking about the dependent samples t-test. All right. So before we get to running the test, let's talk about how we can write our null and our alternative hypothesis. Now we're focusing on just this column here, the column of differences here. And we're not looking at these first two columns separately. That was the independent samples t-test. Dependent samples t-test, you're looking at the differences. There's a sample mean of the differences. So there's a population mean of the differences, and that's given by mu with a subscript d. And so our null hypothesis is mu sub d equals 0. So the mean of your differences equals 0. That's the status quo. There is no difference. And then we can have one of three alternative hypotheses, right? And we're kind of getting used to these alternative hypotheses, right? You can have a non-directional alternative, that's mu sub d does not equal 0, or you can have, and of course, I have the same things here. Sorry about that. Mu is less than 0 and mu is greater than 0, or greater than 0 and less than 0. All right. In order to gather evidence for our null and for our hypothesis test, we're going to need our sampling distribution, our test statistic, and we can use that test statistic to get our p-value, right? All right. And so x bar sub d, based off of the last slide, is our point estimate. Our standard error of the mean difference, x bar sub d, that is given by this notation here, SD sub d. And that is your sample standard deviation of your differences divided by the square root of the number of different scores that you have there, n sub d. All right. That distribution is approximately normally distributed, but since we're using sample data in our standard error, we have a t-test statistic. Our t-test statistic is just x bar sub d divided by the standard error. The degrees of freedom of that t distribution is the sample size, the number of differences minus 1. With that test statistic, we can go to this t distribution with this degrees of freedom, and we can find our p-value based off of the alternative hypothesis. If our alternative hypothesis is non-directional, we get the area under the curve on both tails of that distribution. If our alternative hypothesis is greater than, it's going to be a right-tailed p-value, and if our alternative hypothesis is less than, then we're going to have a left-tailed p-value. If our p-value is less than or equal to alpha, we reject H naught. Otherwise, we're going to fail to reject the null. All right. just as our independent samples t-test had assumptions, those required characteristics of our data in order for us to appropriately use our hypothesis test, our dependent samples t-test has assumptions as well. One is that our sample, we need to have dependence in our data. That means each group is dependent via either matching or repeated measures. And repeated measures is when you use the same individual and you give like a pre or post test. Because the groups are dependent, the n of each group is always equal. And so if you have like a pre-test for one individual and you don't have the post-test, one method to accommodate for that is to get rid of that individual's score, so remove them from the data. All right. And then the main assumption here that we're going to want to check is the normality assumption, right? And the normality assumption is that the differences are approximately normally distributed, or either we're going to have a large sample size. That means our number of differences is greater than or equal to 30. So we have 30 pairs or 30 matches. Once that is the case, we can appropriately use and draw conclusions about our hypothesis test. And so let's do that for this example here. So since we're called the flipped classroom example, we're going to test the hypothesis that the flipped classroom will have an impact on average study time outside of the classroom using a significance level of 0.05. And so I'm indicating here in this slide that my differences are going to be calculated by taking the amount of study time outside of the classroom for the traditional instructional method and subtracting from that the average in the flipped classroom. All right. So my null hypothesis is that mu sub d equals 0, and my alternative hypothesis is that mu sub d does not equal 0. I'm just seeing if it has an impact. Does it impact? Meaning, is this difference significantly different from 0? I'm not saying significantly greater than 0. I'm not saying significantly less than 0. I'm saying significantly different from 0. All right. So one of the first things we're going to do is we're going to look at how our data are entered into JASP. And so I'm going to go to JASP and I'm going to open my data where I have it saved on the computer. I call this flipped classroom. All right. Notice my data is given to me in two separate columns. The first column represents um, the one group in the pair, and the second column represents the second group in the pair, right? And so I have traditional and I have flipped. Now I'm ready to run some descriptives and also run some checks of my assumptions. Notice here, instead of using the dependent samples t-test, I'm going to use the paired samples t-test. When I do that, I'm going to uncheck this. So I just like doing that first. I don't know why. But what I want to do is I'm going to enter the groups into the box that says variable pairs, right? So I'm going to enter traditional. And notice I can also enter another group here. So my traditional is here, and the pair of data that aligns with that is in the flipped column. So I put those in that manner there. Now, if you wanted to switch the order, for instance, you can put flipped in there first and traditional in there second. But I'm not going to do that because I did traditional minus flipped. So you can always change the order. Honestly, your p-value and stuff is not going to change. The only thing that's going to change is the like your the sign, like whether it's positive or negative. When you switch an order when you have subtraction, the only thing that changes is whether a value is positive or negative. Now I'm going to look at some descriptives here. I have the mean for my traditional. I have the mean for my flipped. I know my sample size, so I have the same number of observations in each group, so I don't have any missing data. I can see that the traditional has a larger mean than the flipped. I can get the standard deviation and some other things. What I'm going to do now is I'm going to do some normality checks, right? Notice here my sample size is 10 for both of these groups. So I have, when I look at the differences, my sample size is going to be 10, right? Because I have pairs. And so my sample size is very small. And so I can't use the central limit theorem in this case. So if I don't know that the amount of time, study time outside the classroom has traditionally been normally distributed based off of previous studies, then I'm going to make sure that my sample data shows evidence that is from a normal distribution. And so one thing to do is to do a QQ plot of the residuals. And so I'm going to check that. JASP is working. And remember, I said that this plot is a scatter plot. These theoretical quantiles would be values of my data. So what my data would be if they were in fact from a normal distribution. And these standardized residuals are kind of standard ways that we can standardize our actual data, what they would actually look like in general. And if our data are from a normal distribution, then the scatter plot, the points would lie directly on that line because the x-axis has those values directly from a normal distribution, right? Now, because we have some sampling variability and our sample size is small, we're not going to get a perfectly straight line. However, none of the points are extremely far from the actual line. And so this shows some evidence that my data are from a normal distribution. Now, this is objective. Someone may look at this and say, oh, this point right here is a little too far off, or this point right here is a little too far off. I'll tell you, the smaller your sample size, the more different your data are going to deviate from normality for the simple fact of sampling variability, all right? It's just going to happen. And so to add to this assessment of normality, I am going to do our Shapiro-Wilk test, which is a hypothesis test with a null hypothesis that our data are from a normal distribution. The alternative is that the data are not from a normal distribution. I'm going to compare this p-value to a standard alpha of 0.05, and just as we would do with any of our other hypothesis tests, Since our p-value is greater than an alpha of 0.05, we would fail to reject the null hypothesis that our data are not normal. So, but basically what this test is saying, since this p-value is greater than alpha, we don't have enough evidence that the data are not normal. So we're going to continue to assume that the data are normal. And there's a note once again to remind you, significant results suggest a deviation from normality. All right. So from both the Shapiro-Wilk test of normality and our QQ plots, I have evidence that these data are from a normal distribution. So I can move forward in conducting a hypothesis test. Now, I want to note here, remember I said in the last video, if our data, our sample sizes are small and our data are not normal, we're going to want to use a non-parametric test. All right. I said that really quickly, and it was the Mann-Whitney test in the last video for the independent samples t-test. All right. A non-parametric test, there are many characteristics of them, but they don't, we call them non-parametric because they don't have a parametric distribution. All right. Our parameter that we're looking at when we're looking at either an independent and a dependent samples t-test is the parameter mu, right? Mu is a parameter, and that parameter has a distribution, the normal distribution, right? So all of the tests that we're kind of focusing on this course, these are parametric tests. The one sample t-test, the independent samples t-test, the dependent samples are what we're using now, the paired sample t-test. These are all parametric tests because it focuses on a specific parameter with a specific distribution, the normal distribution, right? But when we don't have evidence, large sample sizes, and evidence in the sample that the data are from the normal distribution, we are going to want to use a non-parametric test. Well, the non-parametric test that we would use in cases where we want to use the dependent samples t-test is given here in this screen here, which is the Wilcoxon signed rank test. Now, in a longer semester course, we would take some time to learn about this test, a lot more about this test and how it's created, what its test statistic looks like, and things of that nature. But we don't have a lot of time in this short 8-week course to get there. And so just know that that is an option for when our data are not normally distributed and we have a smaller sample size. All right, this example, we can move forward with our t-test for the dependent or paired sample case. All right. And so with that, I think I did make some notes in our slide, kind of summarizing all of that. These are our normal assumption checks. It says based on an approximate linear pattern in the normal QQ plots and an insignificant Shapiro-Wilk test of normality, the normality assumption is satisfied, right? So we had to make sure that we check normality. And of course, we already know that our sample, our two samples are dependent because they are measurements from matched pairs, all right? So now I'm going to go to JASP and I'm going to do my, let me make sure I remember what my null and alternative hypotheses were, right? So we're going to use students t-test, and it's that the difference is not equal to 0, right? And so I'm going to use student, and notice it's giving me measure 1 does not equal measure 2. So that looks kind of like the independent samples t-test, but remember the independent samples t-test uses the term group 1 and group 2. This is using measure 1 and measure 2 because you can think of it as one single group, but you're measuring the individuals on 2 different measurements, right? Because it could be one person that's getting 2 measurements, or it can be a pair and the pairs are matched. So it's almost like you're getting one person measured twice again. All right. So here's my results for my hypothesis test. I'm using students t distribution. There's my alternative hypothesis. Here, they're reminding us how we're doing the subtraction for our difference. That's traditional minus flipped. I got my test statistic t, My degrees of freedom, number of pairs minus 1, and my p-value here is very small, right? It's p less than 0.001. All right. And so if I go back to my results, I can see that since p is less than 0.05, if it's less than 0.001, it's definitely less than 0.005. That means it's very significant, right? That means we want to reject our null hypothesis. We're going to reject the null and say there is sufficient evidence to conclude that the difference in the amount of time spent studying outside of class between AP chemistry students taught traditionally versus those with a flipped classroom is significantly different from zero. That means that teaching method is associated with study time. Okay? Teaching method is associated with study time. Now, I'm using the word associated here because this isn't a true experiment where we had a random assignment to either the traditional teaching environment or the flipped classroom environment, right? That would indicate that teaching method um, causes differences in study time. But I can't use causal language, and so I can say that teaching method is associated with study time. Here's an example of a write up in APA format. You can pause that and read that if you would like. But these are the hypothesis test results. Notice here that when we were doing the independent samples t-test, all of that variability, that subject to subject variability, clouded what we really, really wanted to see, which is the impact, or in this case, the relationship that the teaching method would have on the actual amount of study time, right, on average, right? But when we did the paired samples t-test and removed that subject to subject variability, we ended up with a significant result. Now, how significant is that result? We're going to have to look at practical significance, which means we can calculate effect size. So let's go to our effect size measure, which is most often used with the paired sample t-test, and that is Cohen's d. All right. Cohen's d in this case has a slightly different formula. It is x bar sub d divided by the standard deviations of the differences. Please note that the formula that your textbook gives is incorrect. This is the correct formula for Cohen's d that aligns with research using the paired sample or the dependent samples t-test. All right. X bar sub d divided by the standard deviation of the differences. All right. It is in standard deviation units, so it is a measure of the magnitude of the differences in standard deviation units. All right. We have the same interpretation of the actual value of Cohen's d, and I do want you to know that this can be any value. It can range in absolute value. It can be any value. It can be greater than 1, greater than 2, greater than 3, greater than 4. But we usually indicate a small or a weak effect at 0.2. Once it gets to 0.5, we say that's a medium or moderate effect. And once it gets to 0.8, we say we have a large or a strong effect. All right. So in JASP, I want to show you how you can get the effect size measure there. If you go to additional statistics, you can go to effect size, and then you're going to see this paired samples t-test. Adjust. Our Cohen's d effect size measure is 3.293. That is a very, very large effect size. All right. So we went from trying to study this using the independent samples t-test and not seeing any significance with that test, right? We failed to reject, to doing this with a dependent samples t-test, rejecting the null, finding that the mean of those differences or the mean difference is significantly different from zero, and the effect size is extremely large, right? That tells us that we should never ever use the independent samples t-test in cases where we want to use, where we should use our pair sample t-test. We need to actually use the dependency because we can't see that effect. Now, that Cohen's d of 3.293 is a very large effect. And so I can say that Cohen's d, which is approximately 3.29, indicates a very large effect size. This suggests that the difference in study time between students taught using traditional and flipped classroom methods is approximately 3.3 standard deviations, right? And we know that those in the flipped classroom, because our t is positive, and when we saw our descriptive statistics, I'm going to go back here. Oh, I didn't show this descriptives, but since our t value is positive and that numerator was x bar sub d, then we know that the traditional had a larger average. When we did traditional minus flip, we got a positive value. So traditional spent a lot more time studying outside the classroom compared to the flipped classroom, right? And that difference was approximately 3.3 standard deviations on average. All right. Last but not least, we want to talk about the confidence interval for mu sub d, right? Remember, all of our confidence intervals are two-sided in this course for what we're going to do in our course. And we're going to have our point estimate. That means our sample mean difference, plus or minus our test statistic. Our test statistic is a t, right? Times our standard error. Remember, this SD here is the standard deviation of the different scores divided by the square root of the sample size number of differences, right? And the degrees of freedom for that test statistic is n sub d minus 1. Remember, this T comes from your confidence level. Most often in educational research, we use a 95% confidence interval. And so if I use a 95% confidence interval, that means if I do this confidence interval construction method over and over and over again, the 95% of the confidence intervals should contain my population parameter mu sub d, right? That 95% is this middle unshaded area. If I do 100% minus 100%, sorry, the 95%, I get to alpha, which is 5%. 5% divided by 2 is 2.5%, or that 0.025, which is saved for both of these endpoints. So the shaded area on either side here are alpha divided by 2, 0.05 divided by 2. That will allow us to use the QT function in JASP and the R console module in order to get the value of the critical value T sub alpha over 2 df equals number of differences minus 1. So once I have all those values, I can plug it into this formula. It's going to give me two numbers, our lower and our upper bound of our confidence interval. Let's go to JASP and add those results to our output here in our paired samples t-test. If you go to additional statistics, location parameter, we're going to do a 95% confidence interval, which is the default. That's what we generally use in education. And so we see our results of our 95% confidence interval here. This is the confidence interval for the mean difference. And so with that being said, we can say we are 95% confident that the true mean difference in study time between AP chemistry students taught using the traditional versus flipped classroom instructional methods is between 0.4 and 0.7 hours. 0.4 is here, 0.7 is from that value there. All right, so that is some information about our dependent or our paired samples t-test. Please be sure to do the practice problems because they'll give you more practice on using real data to provide out I'm sorry, get practice on interpreting the results, obtaining and interpreting the results for the dependent samples t-test. That's all for this video. We'll see you next week.